It's starting, and we are now officially on air. And I'm very pleased to say that we have Professor Marcus du Sautoy, all the way from Oxford, England. You are currently the head of maths at Oxford University, is that correct? And a whole bunch of other titles.
That's right.
Yeah. You're not the head of maths, or are you part of the maths department? What?
I'm part of the maths department, and my other main role is the Simonyi Professor for the Public Understanding of Science, which I took over from Richard Dawkins. So my role is an ambassador for the world of science, which is why I'm very happy to be online with you all, sharing my stories about mathematics and science.
So you're not specifically focused on maths, because I know that you involved in a lot of presenting on BBC with regards to programs that are science related. So you've got a whole range of interests, is that correct?
That's right. I grew up as a professional mathematician doing mathematical research, but then I was very keen to communicate the excitement of doing mathematics to a broader audience, so I started doing writing for newspapers, doing some radio. But then, of course, actually science is a very interconnected world, and although kids at school are learning subjects in sort of little silos in compartments, they do maths, they do physics, they do chemistry, they do history, they do music. Actually, there's so much fluidity between these subjects. So I got this wonderful chance when I took over from Richard Dawkins to be the Public Understanding of Science Professor, which gave me an excuse actually to go outside of mathematics and explore some of the other sciences. So I've had a great opportunity with the BBC to make programs about the brain, about consciousness, intelligence, artificial intelligence. I made a lovely program about measurement. How do we measure the world? We have 7 units of measurement, which we can measure everything. Absolutely amazing. I just made a program about algorithms, which are, of course, extremely important for the way our lives are being run. So, yeah, it's been very exciting to not just stick to the world of mathematics. And the beautiful thing is, mathematics is hiding under all of these subjects. You'll find maths absolutely anywhere.
Well, now, see, this is the interesting part. A lot of people say to me, why is it that we need to even do maths at school? And I mean, I'm sure you can go on and on about that. But what is interesting is that the point that I try to make to a lot of teachers is that a lot of students, if you want to get them to appreciate and enjoy mathematics, you can't teach someone about art appreciation and get them to paint a wall for 3 hours a day.
Yeah, I think
so. In other words, if students are just doing exercise after exercise, they're not going to appreciate the elegance and the wonders of mathematics if that's all they ever get to see.
I think this is a very good analogy. The one I use very often is music. That when you're learning a musical instrument, yeah, you have to do the very technical side of learning your scales, your arpeggios, and that enables you to then play fantastic music. But you get it, you're motivated to put in the hard work by actually listening to real music, and you say, well, I want to play that, or I want to compose that. And I think that is slightly the tragedy of our mathematics education across the world, is that we focus too much on the scales and arpeggios and don't allow our students access to the really big stories. And so that's partly, my mission very often is to try and give students access to some of those bigger stories, and try and fast track it. Mathematics is taught in a very hierarchical way, so you do one step after another, but sometimes you can go to the top of the pyramid, show people the view there, sort of almost helicopter them in. They don't quite know how they would get there themselves, but you show them this is where you could get. This is the beautiful art you could paint, the beautiful music you can compose, and I think that's, for me, very often my mission is to do actually what my teacher did for me, because I was very lucky when I was about 12 or 13 that I just went to a normal state school here in the UK, but I had a teacher who, when I was about 12 or 13, he, in the middle of the class, he went, "Du Sautoy, I want to see you after the class." And I thought I was in trouble, and I went up at the end of the class, and he took me around the back of the maths block, and I thought, oh, I'm really in trouble now. Oh, sorry for the bell. That's my children coming home.
That's all right.
They're coming home from school, and but then my maths teacher said, look, I think you should find out what mathematics is really about, because it isn't about all of this kind of technical stuff we're doing in the classroom, the long division, sines and cosines. It's something much more exciting. And he recommended a few books for me to read, and they talked about Fibonacci numbers, about prime numbers, about topology, symmetry, and I suddenly realized, you know, what an amazing world this is. And what we were learning was the technical language in order to be able to read these big stories. So he really gave me a key to this secret garden, and I just don't know why our education system sort of denies our students access to this secret garden, thinking it's you know, you have to be very well qualified to go in here and walk around, you know. But no, you don't. Actually, I think one can appreciate some of this beauty without having all of the technical tools to be able to create it yourself.
But you do realize that governments are not making it easier. I know that in South Africa we've got a very poor performance record in TIMS, which is the International Maths Competition. But then, of course, there's debate in the UK recently about should we even have formal maths in high school. Is that correct?
Well, this was, yeah.
You've got American Republicans who are denying the science of global warming. I mean, what is going on in this world?
Yeah, I think there were some provocative news items a few weeks ago in the UK about, actually it was countering a move by the government actually to extend mathematics. The UK is actually a bit of an outlier in allowing our students to give up maths at the age of 16. We only have 20% of the student population carries on beyond 16. And actually, majority of countries realize it's so important to language, and a mathematically literate society is going to lead to, you know, a society that is empowered. So actually, our government has suggested that we also continue maths until 18, and this caused a little bit of a reaction by those who don't like maths, who said, actually, you know what, we shouldn't teach it at all. But actually, I was on the radio with one of the journalists, Simon Jenkins, who loves kind of, I think he likes kind of winding us up a bit.
A little bit, absolutely.
Exactly. And I think, you see, I think what's missed, actually, and this is very important, one of the reasons people say this is that, oh, come on, look, beyond numeracy, what do I need? I don't need to know how to solve a quadratic equation. I don't need sines or cosines in my everyday life. Okay, leave that for the technical people, the engineers and things. And to a certain extent, they have a point, because, you know, when have you used a quadratic equation in your everyday life? It's not the actual ability to do that is not terribly useful, but it's the way of thinking that's incredibly useful, and the way of thinking goes beyond just a facility with numeracy and arithmetic. The ability to follow a logical sequence, a logical argument, to be able to understand that there are algorithms like the equation which solves a quadratic equation, which will work whatever situation you're in. That a way of analytic thinking, which is very special and unique, is something that you only get through a mathematics education. And so that's the sort of point of doing this. And I think that's often missed. People just equate mathematics with arithmetic, and then they think, why do I need to know all of these other things? But actually, mathematics gives you a way to really analyze data, to analyze a logical argument, not to be bamboozled by somebody coming at you with an illogical point of view. You're able to pull the thing apart and to use that mindset to be able to really see the truth. And I think, you know, whatever you're doing, if you're in business, being able to set up a kind of set of rules within your business which can cope with whatever scenario you're hit with, that's going to give you power and being able to see in a load of data what's important and what's not. That's the sort of skills that a mathematics education can give you, and what's often not realized by the media or government.
Now, I agree with you, because I'm obviously a big fan of mathematics, but I think that one additional skill that needs to come with mathematics is creativity. We do a lot of problem solving with our kids. We do a lot of thinking outside of the box, because at the end of the day, the top 10 jobs of 2016 did not exist in 2010. So that means 6 years ago, the top jobs today were not there, which means you need to be able to adapt and think outside of the box and cope. So I think maths is also about a set of skills and a set of tools that enable you to cope better. Obviously, you have to be mathematically literate and scientifically literate to cope in today's world because of the technology and things that are going on around you. But it's about coping with new and different situations that you've never encountered before. And a person creatively and logically will be able to tackle things in that way, whereas most people will just be overwhelmed.
Yes, I think that element of creativity is one that a lot of people don't realize is part of them being a mathematician. I think they think it's about following rules and actually being very boxed in. But that was one of the things that I learned as a student through my mathematics teacher and the books that I read. You know, I was very interested in music. I was learning the trumpets at the same time. I loved doing theatre. The world of the creative arts was one I loved being part of. But I also love the world of science, you know, the ability of science to work out where we've come from, where we're going next. And for me, mathematics was this kind of language which fused these two together. I mean, mathematics is very creative, and it requires very intuitive, imaginative leaps into the unknown. And it, as you say, it does require this ability to think outside the box. I think that's really important is being able to change the language, changing the language to be able to take a problem and look at it in a new way, and with that change of language, often what looks very difficult suddenly becomes incredibly transparent. And mathematics is very good at finding new languages in order to articulate structure.
Absolutely. And I mean, for me, I always tell the kids that, you know, it's not really about the destination, it's more about the journey, the process of getting the answer. That's quite delicious. You know, when we're in a classroom environment, we've got, let's say, year 1 and year 2 kids, it's always about, yeah, I've got the answer. They put up their hand and they run up to you and they bring their book. And I say, well, you know what? I don't want to see your answer. I want to see the process that you took to get there, because that's far more important to me. And I'm sure that as a mathematician and as a professor of maths, when you're looking at students, it's that kind of discussion and debate where we look at the methodology of getting there. And on that particular topic, there was a recent announcement of a British mathematician who solved a very well-known problem and won lots of money. Am I getting that correct, or am I mixing up certain things?
No, this is, we recently, as a colleague of mine in Oxford, Andrew Wiles, who just won our version of the Nobel Prize. It's called the Abel Prize, named after a Norwegian mathematician beginning of the 19th century. Abel was one of the creators of the language of symmetry. So this prize is named after him, the Abel Prize. And yes, a couple of weeks ago, my colleague Andrew Wiles won this prize, actually for some work that he did in the 1990s. He was responsible for proving this great unsolved problem, Fermat's last theorem. So this was a problem that was on the books for 350 years. Pierre de Fermat had this equation that he thought didn't have any solutions, and he wrote very provocatively in the margin of his book. He thought he had a proof for why there were no solutions, but unfortunately the margin was too small for the proof, and so it was the biggest mathematical tease in history. And so for 350 years we've been trying to prove Fermat was right, that these equations don't have any solutions. They're actually equations which relate to Pythagoras' theorem. So Pythagoras' theorem, a lot of the students out there will be learning or have learned. So that says that it gives a relationship between the sides of a right-angled triangle. You take the square of the long side, it's the sum of the squares on the two shorter sides. Now, the interesting thing is you can find numbers, whole number solutions to this equation. So, for example, 3 squared plus 4 squared is equal to 5 squared. And so a 3, 4, 5 triangle is a way where all the sides have whole number lengths and will satisfy Pythagoras' theorem. Fermat said, okay, what about cubes? What if I take x cubed plus y cubed equals z cubed? Can I find any whole numbers which will solve this equation? Or what about fourth powers, fifth powers? And however hard he tried, he couldn't find any numbers which, the cubes, if you take two of them, raise them to the cube, add them together, they're not a third cube. But as you say, exactly this, that the important thing is the journey. And I think this is a really important message that you've highlighted for students, that mathematics is not about the final destination. So in a way, do we really care that these equations had solutions or not? No, what we cared about was understanding why they didn't have any solutions. And the journey we went on for 350 years in proving Fermat's last theorem, which culminated in my colleague Andrew Wiles proving that they can't be solved, created the most extraordinary, beautiful mathematics. The mathematics, for example, of imaginary numbers, of elliptic curves came in there, algebraic number theory. In fact, you could say that the cryptography that is used today on the internet, which anyone who's sent their credit card across the internet want to keep that credit card secure, they're essentially using mathematics that got generated in our journey to prove Fermat's last theorem. So that was what Andrew Wiles was awarded the Abel Prize for 2016, which is our Nobel Prize. And it very well deserved. He put in the final piece of the jigsaw, but it took him 7 years, and the work that he did was unbelievable. It really, we were all staggered that it got proved, frankly.
I mean, there've been a lot of, announcements on the internet and people tweeting this and that, and they're going, no, it was a fake article, but I mean, it really now has been proven. In fact, what I find fascinating is that there are a couple of big maths prizes out there. There's the Abel Prize that you were talking about, and then there's the Fields Medal.
Yes.
What is the big difference between the two?
Well, the Fields Medal, the Fields Medal has been going for a little bit longer, and anyone who's watched Good Will Hunting with Matt Damon, the Fields Medal is mentioned quite a lot there, because that's the kind of ultimate prize for a mathematician, is winning one of these medals. Now, the interesting thing is the Fields Medal is restricted to anybody under the age of 40. So when you're over...
Ridiculous.
Well, yeah, it sounds a bit ridiculous, and it sounds as if it's playing into this myth that mathematicians, they do their best work before 40. Now, being over 40, I really have to say it's a myth, because I have to believe that.
Yes.
But actually, if you read Fields, who endowed this prize, his motivation was actually quite sound, because what he wanted was a prize which would inspire further research. And he felt that it was important to reward the young, to inspire them to go on to do even greater things. So that's why, actually, he asked for the prize to be restricted to those under the age of 40. But the Abel Prize is generally awarded to people sort of towards the end of it. So like the Nobel Prize, it's almost a prize for a lifetime's work. But there are some other interesting prizes which students might be interested in, especially because there's $1 million prize for solving certain unsolved mathematical problems. Actually, I wrote a book. This is one of the books I've written called The Number Mysteries. And this book is actually your secret to winning the $1 million, because each chapter is about one of these unsolved problems. So, for example, the first unsolved problem in this book is all about prime numbers. Now, prime numbers are literally like they're the atoms of our subject. They're the indivisible numbers. So numbers like 7, 17, 19, but not 15. 15, for example, is 3 times 5. So these indivisible numbers, I think of them a bit like atoms like hydrogen or oxygen. So, water is made up of 2 hydrogens and an oxygen. Well, the number 105 is built by multiplying 3 times 5 times 7. So they're so fundamental, yet we know for 2,000 years we've known that there are infinitely many of these numbers. That's one of the great proofs of the ancient Greeks. But we do not understand a pattern to these numbers. So they go off to infinity, but we don't have any way of being able to predict where we're going to find a prime. They seem incredibly random. So the challenge, and it's called the reading.
An algorithm that you can throw a number in and it spits out a prime number?
Well, that's the sort of goal, to find some sort of pattern that gives you some rationale for how to find these things. There are kind of algorithms, but they're very slow, and what you want is sort of, you know, like the Fibonacci numbers. So if I give you the Fibonacci numbers, 1, 1, 2, 3, 5, 8, 13, 21, you can go, okay, no, I spotted the algorithm there. What you do is you add the two previous numbers together to get the next one. And so that gives you a nice, simple way of generating all of them. So we'd like the primes. We'd like to think, okay, 2, 3, 5, 7, 11, 13, 17, 19, 20. Okay, what's going on here? What do I do to find the next one? And there just doesn't seem to be some simple sort of equation or simple algorithm. And so that's one of the challenges. $1 million is out there for anybody, first of all, who could understand a pattern, but actually what we genuinely believe is that they don't have a pattern, that they have the characteristic of a sequence of random numbers. And that's why it's so difficult to understand them. So the challenge is, why? Why do they look so random? What is it that's making them behave in this way? And actually, there was a story a few months ago of a teacher at a university in Africa who made the World Service news because he'd claimed to have come up with a proof, and it caused a little bit of excitement for a sort of, I think, for 24 hours, especially because the BBC World Service picked the story up. But it's a notoriously difficult problem. And probably is our greatest unsolved problem because it's about the most important numbers in mathematics, these prime numbers. So that's one of these, they're called the millennium problems. So that's probably the most important millennium problem. And there is $1 million prize for anybody who...
For each one or just that particular one?
There's $1 million for each one. So there were 7 millennium prizes. One has been solved, and that was called the Poincaré conjecture, and it was solved by a Russian mathematician about 2000 and what do you call them? The noughties, the middle of the noughties. This is a problem about geometry. So essentially, it's a problem about what possible shapes could our universe be wrapped up in. We live in a 3-dimensional universe. If you think about the surface of the Earth, the surface of the Earth is a 2-dimensional surface, and it can be wrapped up in different ways. It could be a sphere, or it could actually be a donut, so it could have a hole in the middle, or it could be a pretzel with 3 holes in, or 2 holes. So we understood all the different ways that a 2-dimensional surface can be wrapped up. But we're living in a 3-dimensional universe, so the challenge was, well, what ways can you wrap up a 3-dimensional universe, which would have to be in 4 dimensions to wrap it up? But so yeah, it's quite I could be rude and say a mind. It messes with your mind.
I can say. So what you're really saying is that if people go out and purchase your book, there is a mathematical chance that they could become a millionaire in dollars. Because I don't want to convert dollars to rands, because if you just have $10, you're already a millionaire in South Africa. But I mean, you could make a lot of money from buying a book. And do the chapters help you to solve, or just explain what they're all about?
Well, look, frankly, if I could solve them, I wouldn't have written the book. But that said, let me impress on you that the important thing for a mathematician is not that money. I would personally, I would pay $1 million if I could find out the secret to how those primes are ticking. And I think that's, you know, the ultimate prize is not money. Money would be spent, but the wonderful thing about mathematics is that it lasts forever. Once you've got a proof of something like the being infinitely many primes or a new mathematical discovery, it gives you a little bit of immortality. And money, you can't take money to the grave, but actually you will be able to take your achievement and you will be remembered. Fermat is still remembered today. Euclid is still remembered today after 2,000 years. Andrew Wiles will be remembered today, will be remembered way into the future. So for me, you know, these problems, although they have $1 million prize, the real prize is getting your name on proving one of those great unsolved problems. And this is an interesting point, which is a difference between mathematics and science, because science has a much more evolutionary character. It's the survival of the fittest theory. So, you know, one theory might be, you know, we thought the universe was kind of contracting into a big sort of crunch. Now we understand it's expanding. Now we understand the expansion is, in fact, accelerating. So we produce new models of the universe, and the old models just fade into, you know, they're not relevant anymore. Mm-hmm. That doesn't happen in mathematics, and that's the power of proof, that in a way we're building this huge, great big pyramid, and what we're still teaching kids what the ancient Greeks proved 2,000 years ago. But think about the science. We're not explaining the science that they discovered. You know, they thought matter was made out of earth, wind, fire, and water. Now we realize that, you know, it's made out of different things. And I think mathematics, there's a permanence about it, which I think I was really drawn to as a student. I wanted the security of knowing when I proved something, it would be there forever. And that's something really special about maths, which has a different quality, I think, to the other sciences.
Okay, but now what worries me at the moment is why the world is moving away from mathematics. I mean, if you look at the technology that we're using and how much maths is involved, we obviously promote coding and that type of thinking because we feel that that's also a mathematical way of solving problems, just using a different language. We're starting to see that this whole technical world around us is requiring more people who are scientifically and mathematically literate. Yet, countries tend to be moving away from the importance of maths and moving into other things. Why do you think that is the case?
Well, I think it's a very dangerous move because, you know, we are in such a data-rich age, and those who have the tools to understand that data and make predictions into the future, they're the ones with power. So it seems a crazy kind of message to send out that you know, to move away from these scientific and mathematical tools, because, you know, you can see the people with power today are those who understand the numbers. And as you say, all the technology that we use and facilitate our lives, you know, the fact that I can type something into Google and it can immediately find the website that I'm after. I mean, that it's not magic, it's mathematics. That is, you know, there aren't Google elves sitting on the other end of the computer looking up things. Oh, he wants to know about the Riemann hypothesis. No, it's an amazing use of the mathematics, actually, of eigenvalues of matrices is able to analyze these networks. So I think, you know, a lot of kids realize that the things that they use, the technology, Facebook, things like Google, the smartphones they use, you know, the best smartphone is the one with the best mathematicians who created it. But you're right. Some people will say, okay, but, you know, I feel disenfranchised because I don't understand this. And, you know, you don't need to know the maths to be able to use your phone. I mean, that's certainly true. But I think, you know, we have, this is a lot of my role as a professor for the public understanding of science, is trying to create a dialogue with society that is perhaps initially rather nervous, rather skeptical, rather suspicious of this world because they think they don't understand it. And it's important that they understand it because the political decisions are in their hands. They're the ones who vote for governments who will make big decisions on, well, climate change. You know, that's a mathematical problem, basically. It says, look at the data, look where it's going. There's a very strong trend here, and you know, you can't ignore this, and you have to do something about it. And the solutions, the solutions as well will come from finding ways to manipulate those, you know, the output of those numbers. You know, what can we do? What is it that we need to turn down? Some things won't be effective. You can turn down one dial and it doesn't do anything. Well, you've got to know that relationship. So it's very important to me, and I think that's, you know, I think it was very far-sighted of Charles Simonyi in 1995 when he set up my professorship. He realized we are in a scientific age, and unless the society understands the science, they don't have to do the science, but they need to appreciate its impact on us. Then you know, we're going to be an impoverished society. So I think it is very much an an important role of being a scientist is to try and counter this trend, which actually, you know, I think it's very often coming from governments and maybe from business and maybe from parents as well. You know, we've got people joining us from all over the world, and there are different attitudes across the world to mathematics and science. I mean, we have people joining us from India. Now, India is somewhere that I love going to because I immediately get a respect as a mathematician, and I think parents instill that respect for mathematics as a tool to empower you, to take you out of poverty even, to be able to really fulfill your life. They really realize that mathematics is an important tool. Whilst, you know, here in the UK, I'm often embarrassed by how often people will respond to my statement that I'm a mathematician by saying, "Oh, I was rubbish at maths," almost wearing it like a badge of honor. I mean,
I know. I hear that all the time as well.
Yeah, you must. And it's a rather disappointing thing about the West more, I think, than say somewhere like Asia and India, where I think, you know, a lot of these, take somewhere like Singapore or Korea, South Korea, you know, these countries have shot to the top because they realize the importance of a scientifically literate society.
Well, what interests me though is, you know, someone like you are very au fait with communicating with the public about scientific concepts and mathematical concepts, and I've seen some of your online presentations, and you definitely believe the stuff that you're selling, which is a good thing, because, you know, I mean, if I watch you, I can see that you are convinced about what you are saying, and that's important. But then all of a sudden, you put something on to social media, and because people don't have the right filters, they see certain things, they misinterpret, they share the wrong information, they don't know that certain things are incorrect or correct, and their common response is, but if it's on the internet, it must be correct.
Yes, I mean, this is, you know, this is why we need multiple channels in order to be able to kind of check, recheck, make sure that, you know, there isn't one message which somehow, just because of some quirk, becomes you know, the thing which everyone thinks is true. So I think that's why it's very important that everyone plays a role. You know, one person can't do it all, and you know, part of my job is trying to encourage my fellow scientists to step up to the plate and also play their. I think, you know, one of the good things about the university system and the scientific community is that we are generally impartial. We believe in truth, and that's our motivating drive. We don't have to worry about the fact that a company needs profit or that a government is forcing us to do things. And so I think very often that's a voice you can trust. And it's been shown that there's been a lot of research done on what voices should you trust. And often university scientists come out high because there's a belief that, well, we don't have any paymasters that we have to kowtow to. That changes if you take a scientist maybe that's working within a more corporate framework where they have restrictions on what they can communicate, or so I think.
I mean, there are some scientists, for example, who might work for certain companies, let's say a beverage, I won't mention any names, but it rhymes with Coca-Cola, and this particular company, they, for example, might pay a scientist a certain amount of money towards research, and miraculously his findings show that this particular product is not harmful to people. Yeah. And he's using science to demonstrate this, or not.
Yes. Yeah, I think that's why you really you have to question everything that you read, because you need to know, well, what's the background to this, because and you know that from reading the newspaper, there seem to be so many contradictory stories, and journalists you know, generally they do a great job, but they also are after selling newspapers, and so they will pick a story up which has got a great headline, and often they might twist that headline. I mean, the one that I often wonder, are journalists doing this deliberately or not? But, for example, eating bacon in the morning can double your chances of getting pancreatic cancer. Now, it's really scary. But then you look at what it means. What does it mean? Well, okay, so there's maybe a 1 in 1,000 chance that somebody at random will get pancreatic cancer. By doubling that, that goes to a 2 in 1,000 chance. Well, that's still pretty small. And you might say, I really love bacon, and I'm prepared to take that risk of going from 1 in 1,000 to 2 in 1,000. But when a news headline says you double your chances, that sounds really horrific. Sounds like I'm almost guaranteed to get. So I think that's again coming back to why mathematical education is so important, because it allows you to ask the right sort of questions of interpretation of data like that. It is true. It's not a false statement, but it implies something that you don't is not actually there. So I think it's really important to question what your sources are.
Absolutely. I mean, one of the things that my students said to me is, mean, median, and mode. I mean, what's the big deal? Why do we even need it? And I said, what is interesting is that when a company, let's say a man owns a factory, or a woman owns a factory, you can use woman too because women can own factories. A woman owns a factory and she employs 100 people, and the average salary in that factory is, let's say, £50,000 a year. You would say that's a pretty decent factory. But the minute you start analyzing what the most common salary would be, all of a sudden that starts changing to a much smaller number. Exactly. And then you start looking at the outliers, what is the maximum and the minimum, you start to realize that they were not lying when they said that the average salary was a certain amount, but the fact is that he's paying or she's paying a pittance to the workers, and that's what we don't really get to see.
Yes, exactly. So all of the and here we are in an age of data, of big data, and being able to realize what are significant patterns inside there, what are actually patterns that aren't real because they're just what you would expect from a random process. These are really important because you can often get completely taken in by something that looks like a strong pattern, but actually is something that is really just randomness. Here's an interesting example. The Bulgarian National Lottery in 2009, I think it was, 6 numbers came up on the Wednesday, and then the same 6 numbers came up on the Saturday. And everyone said, "Whoa, this is ridiculous! That it must be some sort of somebody cheating this." It's and an investigation was initiated. The Bulgarian government said there's corruption at the heart. But if you analyze the numbers, the number of lotteries that are going on across the world, been going on for decades, actually, you would expect this to happen once in all of this time. It's not unusual that these, but of course you notice the strange spikes, and you don't realize that that's just part of a whole number of possibilities. So actually that ability to question what's real, really significant, what isn't. Here's I mean, there are some classrooms which have joined us, and people who watch later may have a classroom. Here's an interesting kind of rather counterintuitive fact. How many people do you need in your classroom for there to be more than likely chance that 2 people in that classroom will have the same birthday? Now, most people's intuition is, wow, gosh, well, there are 365 days, the possible birthdays. What, you want 2 which are going to be the same? Well, maybe I need 150 or something in there. But what they're thinking about is they're thinking very personally. They're thinking, what's the chance of somebody will have my birthday? Well, yeah, if you have people coming into the room one after another, the chance they'll have your birthday, yeah, you probably will need half the year number of possible birthdays. But no, I'm asking for 2 people with the same birthday. So, I challenge you, there are some classrooms I can see out there already go around the classroom and see whether anybody shares the same birthday. Because it's remarkable that you only need 23 people in the room, and there's more than likely chance that there'll be some combination where 2 people have the same birthday. That's an extremely small number. And so, but to understand that you're going to get a coincidence even with 23 people, it is, you know, that can be very empowering. Here's a nice little football, but I know we both share a love of football. Maybe not of the same football team, but
a real football team. But that's okay. That's okay.
But every Saturday, you know, I'm a big Arsenal supporter, so actually I've got my Arsenal cup here. It's we have on the London Underground. We have these wonderful labyrinths that were made by an artist, Mark Wallinger. So every tube site has its own particular labyrinth. So whenever anybody comes to London, look for these labyrinths. So this is the labyrinth at Arsenal Tube. But whenever I go to Arsenal or anybody goes to their football match, there are in fact 23 people on the pitch. You've got 11 on one side, 11 on the other, and the referee in the middle. So the mathematics means that, you know, of all the matches that happen on a Saturday, half of them will have 2 people with the same birthday on the pitch. Now that's really staggering. And I did an analysis one weekend, and sure enough, you know, it was like there were 10 Premiership matches, 5 of them had 2 people with the same birthday.
That is just phenomenal. Now that's what I love about the quirkiness of mathematics, that you can actually discover things which are quite incredible. Now I know that Mr. McNulty's class in the US, there were a couple of questions. So let me just have a look at what those questions were. The first one was, what are some of your hobbies besides maths? And before you answer that, I just want to lead into that. I know that you've done a couple of BBC programs about the brain, and there was one program in particular that shocked you, that a decision is made 7 seconds before you make it. Can you tell us a little bit about that, and also about some of your involvement with the programs you've done on the brain?
Yeah. So this has been one of the exciting things which have come out of this job, being the professor of the public understanding of science. To be able to go and make programs about the brain, to be taken to labs around the world. And the one that really shocked me was actually about free will. I went to John Dylan Haynes' laboratory in Berlin, and he's investigating when do we consciously become aware of a decision we're making. And so what he did, he had me in an fMRI scanner, and he had me just randomly, I had 2 buttons that I could press, one with my left finger and one with my right finger, and he just asked me to, at random, make a decision about, oh, I'm going to press my left finger down or my right finger down. And I had letters being scanned across my eyes, and so I could see the letter that was in front of me when I consciously made my decision to go left or right. What was striking was that with the fMRI scanner, John Dylan Haynes could see that I was going left 6 seconds before I had consciously been aware that I was making that decision. So my body was already going left, and his consciousness could know before my consciousness what I was going to do. So that impression that I had free will about going right or left, it seemed like, no, the decision had already been made before it was ever thrown up into my conscious brain. And 6 seconds is a long time, you know. My brain decides,
we're talking 6 seconds.
Yeah, my brain decides to go left. 1 elephant, 2 elephant, 3 elephant, 4 elephant, 5 elephant, 6 elephant. Now it's thrown up into my consciousness, and I go, oh, I think I'm going to go left. So that was one of the most exciting projects. Another one I did was I made a program about artificial intelligence. And I think that's a really exciting area at the moment. Maybe some of the people watching this were aware of this exciting match between a computer and the Korean playing the game of Go. The game of Go has always been regarded as a sort of almost an impossible task for a computer. There are so many different scenarios, and it's something that requires a kind of intuition, a very strong visual sense, pattern recognition, something the human brain is very good at. But using this thing called machine learning, they've now managed to create a computer that beat the best the world has at the game of Go. And so this program I made about artificial intelligence was really exciting, just seeing what the future holds. And in that, actually, they asked me to do some very strange things in these programs sometimes. I mean, I had my brain scanned a lot, but in this one, they wanted me to learn how to walk a tightrope. And the idea is, how plastic is the brain? How quickly can a human brain learn something? And so I was taken along to this circus school, and I had an afternoon with this circus instructor. And it took some time. I mean, they did a lot of filming, and my director was getting a little bit dismayed that, is he ever going to get across this tightrope? But after 4 hours, my body had learnt enough to be able to get from one side to the other. And that, the brain and humans are extraordinary at being able to learn new things. But, computers with this machine learning are not too far behind. Anyway,
well, there was the big case of Microsoft putting out their AI bot, and unfortunately, it was quite reflective of the youth of today, which was quite scary.
Yes. You see, I think that was a very interesting case. So one of the kind of challenges in artificial intelligence is this thing called the Turing Test. So can you make a computer that it can interact with a human such that the human doesn't know that this is a computer algorithm but thinks it's human? And so there are a lot you can download. I've got one on my smartphone. It's a kind of if you just talk to it, and actually you're training it. The conversations you're having with it are being banked for the next conversation it will have. So the people online realize this. So they had this, Microsoft had this sort of algorithm which was tweeting, and people kind of basically, well, I mean, they didn't hack it, but they basically said, okay, this thing's learning from our interaction, so let's really mess with its mind, interact with it in a what turned out to be a very racist, anti-Semitic, anti-feminist, and suddenly this thing's tweeting the most horrific. They had to take it offline. So so that's very interesting. You see, so that's a real. I mean, I think it's a good benchmark for where are we with artificial intelligence. This thing could not assess that it was being led astray. Was well, humans also get led astray.
The filter, no, I mean, that's exactly what it was. It didn't have enough intelligence to filter what was inappropriate and what was appropriate, and subsequently it failed that test in major ways. But AI is growing, and do you think using AI we will be able to solve some of the biggest mathematical problems that humans have not been able to solve?
That is a really great question. And you know what? I had always held up the game of Go as a perfect example of what mathematics is like, because a game of Go is quite logical, but it requires these kind of creative, imaginative leaps and an ability to assess just sort of structure without perhaps knowing how to join all the dots up. And if I'm making a mathematical conjecture, very often I need to have almost a feel for what's out there, and I don't know how to get there yet, and I will then later try and put the pieces together. So I always said, computers can't play Go. Go's like doing maths. Now a computer can play Go and can beat the best. So I think there's a very interesting future. What role will computers play in finding proofs? Certainly computers have been used already in checking proofs and in perhaps filling in bits of proofs. We have this very famous thing called the 4-color map problem. So if you draw a map of the world, you always find that you can use 4 colors and no more, such that no two countries that have a border have to share the same color. But in order to prove that, there's a beautiful sort of analysis, but at some point you get left with a huge number of maps, and you just need to, a human would take just forever to check them all, probably make a mistake. The computer was then used to complete the proof by checking these finite number of possibilities. But that, I wouldn't say, is a clever use of a computer. It's just using the computer to mechanically go through and check these things. What you're asking about, and what I think will be the exciting future, is can a computer come up with those kind of creative leaps to come up with the idea of how to get to that point where you need to check this finite number of things. And that, I think the jury is still out about how creative a computer can be mathematically. But already, this program I made, we can see computers being quite creative artistically. In the film, we featured something called the painting fool, and the painting fool was able to actually create quite exciting art through the algorithms that it was using and generating. The other one was music. We had an artificial intelligence kind of saxophonist who'd taken kind of the musical world of a human saxophonist, had distilled algorithmically what made that person tick, and then was able to create new things. And the saxophonist that was used said, wow, I didn't realize that was in my repertoire. The computer had shown it things that he could do which he didn't realize was possible. I'm just going to get, my computer is without any power, and I can see my battery.
Plug in, that's cool, that's cool.
Yeah, so you gather some questions while I just go and get some more power.
No problem, no problem. So while Marcus is getting power for his PC, I've just come up with a brilliant Kickstarter project that hopefully Marcus will join me on. We are going to be developing a device that can read your mind 6 seconds before you make a decision. So can you imagine when you are playing cards, when you are flipping a coin, if you're playing rock, paper, scissors, if you are asking your children what they would like for dinner? I don't know if you can hear all of this, Marcus, but we are going to make a lot of money. I'm telling you now, this Kickstarter project is going to, we could retire. So we're going to make a project where this device reads your mind 6 seconds before you make your decision. And we're going to use that to then make decisions before you do, and that way we could make money. I mean, I could go along and ask you, what, okay, rock, paper, scissors, whoever wins gets 10 pounds. And before you even make that decision, this little thing will flash up what I should do to beat you because it knows what you're already going to do. Boom, we are going to retire.
Yeah, it could be the future. I just warn you that this the thing that they were using was a massive, great fMRI scanner, and you have to sit very still in this thing in order to scan the brain. And so playing rock, paper, scissors at the moment inside that thing probably would. And actually, to tell you the truth, they need about a month to analyze the data to really know what's going on. So we're still quite a long way.
In a few years' time, we will bring it much smaller. You'll be able to wear a little helmet on your head, and we'll solve that problem.
No, I mean, I think
technology.
Yeah, the challenge of knowing what's happening inside somebody else's head, I think, is one of the great mysteries of science. So.
I see Mr. McNulty and his class are busy waving. Let's have a look. Are you waving because you're going, Mr. McNulty? They're busy waving, and hopefully we can have some others join us as well.
Yeah, I'm afraid we have to head out, but thank you very much for the opportunity.
Yeah, thanks for joining us.
You're welcome.
Okay, guys, say goodbye.
And I know that was the 8th graders there out in Newtown, and we might have Miss Harris join us with her grade 5 students. I'm not sure. She was just messaging me now because they've been watching it live on YouTube. So what interests me though is that I don't know if you go to all the science festivals, but I go to all the science festivals and we go around and we show people how to get excited about numbers and science as well, and because we're doing all these interviews, we get to share the passion of all these science communicators with as many people as possible, because it's not about painting walls, it's about being exposed to everything else. So, and Lynn also says she has to go, so thank you very much, Lynn, for joining us. Bye-bye. And, I mean, there is a challenge out there for us to reach as many people as possible. There is a challenge when the people on top are starting to make decisions about climate change and things like that are not intuitive or common sense, because apparently common sense isn't as common as we thought it was. And what I find interesting is that our job is getting harder, and it should be getting easier. But I know that on TV, I don't know how you measure it, but in South Africa, there was some statistic that if you take the number of TV programs that are played on our channels and you calculate the percentage that are science and maths flavored, I think it was something like 5% or 7%.
Well, that's quite
I don't know
high.
what it's like in the UK. Well, I mean, that's just insane.
Yeah.
There should be way more. You know, if you expose kids to that sort of thing on TV, because we know they're already watching TV, we might impart the beauty and excitement of science and technology because we've got an audience willing to watch.
Well, I tell you that BBC not because they want to be helping education. They make science programs because there's an appetite for it. And that's what I think we need to tap into. Actually, people really want to know these scientific stories. They're, as you say, they're amazing. And you know, there are people coming along to these festivals who want to hear the stories and find out the interesting science that will impact on them in the years to come, or just see, you know, science that is for science's sake as well. And so I think there is an appetite, and you know, I'm always just. I think it's wonderful the sort of things that I've managed to make with the BBC. You know, we made this wonderful series, The Story of Maths, which looked at the whole history of maths, 4 one-hour programs. I made this program, The Code, you know, understanding the mathematics that lies underneath nature and that we can exploit in our sort of technological world. So I think, you know, that there are some crazy programs out there. I agree, which you wonder how on earth did that get made. But I think you know, there is exciting new channels. I mean, for example, what you're doing here. You know, we're able to make our own sort of platform to communicate science, and you know, there's a chance for a lot of scientists to use the new media that's available to actually, you know, shortcuts this need to go to a big TV producer. And then the sort of lectures that you can see online on YouTube, it's you know, there is I think the potential to tell some really great stories. So I don't think the future is that bleak.
Now, I mean, what I would like to obviously end off with, because I know that you've got another engagement to run off to, is, you know, you started off and you were not a mathematics person. You never planned to go and study maths at university. What sort of advice do you give young people that if they want to get a taste of the excitement of mathematics, what are the things that you would suggest that they do, you know, what I would call the route towards heading in a mathematical way? What sort of rocks should they step over along the way that might encourage them to enjoy it more?
Yeah, well, I think in a way that's quite a difficult question to answer, because what I believe is that mathematics is hiding everywhere, and you know, people have different interests. They might be music, it might be art, it might be theatre, it might be science, it might be technology, and I think that it's whatever you love is to sort of ask the question, you know, well, is there some mathematics hiding here? Now, sometimes it's difficult to know the answer to that, but I suppose, you know, I don't want to plug my book again, but in a way, this book here, I wrote this book coming out of the Christmas lectures that I gave for the Royal Institution, which actually was one of the things that was responsible for me becoming a mathematician. I went to them in 1978. They're given by the Royal Institution in London. They were started by Michael Faraday in 1825. In 1978, which is when I went, it was the first they were ever done on mathematics. And I came away from that, this mathematician, Christopher Zeman, just showed me such extraordinary stories. And I got the wonderful chance in 2008 to deliver my series of lectures. And they're actually online. You can go to the Royal Institution website. And my brief actually was to aim at 11 to 14-year-olds. And 11 to 14, I find, is an age when actually, you know, a lot of kids come out of primary school quite fired up, you know, about playing with numbers, numeracy, and then they get hit with this, as you say, painting the wall with a single color, and they become bored and they get turned off. And so this is kind of my manifesto, the number mysteries, for what I wish kids were exposed to sort of from 11 onwards, and it kind of tells the stories of mathematics in everyday life, mathematics in architecture, in music, And so I suppose this is the book. You know, my mathematics teacher inspired me when I was 12, 13 by recommending some books that really opened up this magic garden, as I said, of the world of mathematics. And this is the book that, you know, the kid behind the block, I would give him this or give her this and say, you know, here are some of the stories of where you can find maths in really unusual, exciting places. And so my hope is that, you know, this book and others like it, there are lots of great mathematicians out there telling these stories. Those are the places that will kind of unlock this magical world, I hope, for others.
We hope so too. But now, one final question. You've got a new book coming out. Are you allowed to know anything about that?
Yes, it's coming out in the middle of May. It's called What We Cannot Know. And this is it's quite a philosophical book in a way. It's asking, are there any questions in science that by their very nature we know we will never be able to answer? Perhaps there aren't any. Science is being incredibly successful. Perhaps we could one day answer all the questions that there are about science. So, but I was interested perhaps to rein in that enthusiasm, ask, well, okay, are there any questions we can say now we'll never know? For example, you know, is the universe infinite? Could we ever know
the number of grains of sand on Earth?
I mean, we've got this bubble surrounding us. Information travels at the speed of light, no faster. That we cannot get information from certain parts of the universe, and because the universe is accelerating in its expansion, there are regions of the universe which will never communicate with us. So could we ever know that the universe is infinite? So the book is looking at different questions across the sciences: cosmology, quantum physics, neuroscience, biology, and mathematics, and asking, can we say now that these are questions that we will never know the answer to? And if they are, how do we cope with that?
Sure. So, that's pretty exciting. And when are you officially doing the launch?
So the official date is May 19th, and so I'm doing some lectures around then. So there's one. My kind of official launch, in a way, is at the Mathematical Institute in Oxford. I'm giving a talk, I think, on the 12th of May, and that's kind of my kind of when this book goes out. And you know, I've been living with this book for the last 3 years, and I'm looking
to actually breathe.
Yeah.
Wow. Okay. Well, we wish you all the best of luck for the launch. We want to say thank you very much for giving up your time. I know that this is family time, and you're also running off to other engagements, but thank you so much for helping to share the passion of maths and science, and we look forward to other programs that are coming out. You see, the internet's a wonderful thing. I can watch all the things except for that one series. There was a series you did where there was a challenge or a code each week. That's I couldn't get access to, but it's just a matter of time. It's, you know, we might think that right now we can't, but technology is an amazing thing. So thank you so much for sharing your time with us and your passion for maths and science. And we look forward to seeing maybe you as the next winner of another prize, since the others have got the 21 plus VAT age limit. Maybe there's another prize out there that will be able to celebrate the excitement of sharing your passion for science, as opposed to just a mathematical discovery, but more about the sharing of mathematical discoveries, which would be lovely.
Yeah, well, thank you very much. It's been great to join you and to share the stories with you.
Okay, cool. Thank you so much, and I'm just going to stop the broadcast.